Okay, welcome back. So today we're going to continue on with Chapter 9, and now we're going to start confidence intervals, the hypothesis testing involving the mean, right? So confidence testing involving claims about the mean, but this time we're going to assume that we don't know sigma, the population standard deviation. Now this is 99.9% of the cases out there. This is what we're going to deal with. We're going to deal with where we don't know the population standard deviation. So what do we do in that case? Well, in that case, we're going to end up using a t-distribution. Just like in confidence intervals, if we don't know sigma, we use the t-distribution instead of the z-distribution. So in this case, when we do hypothesis testing, we're going to do a t-test on the calculator instead of a z-test. So I'm going to walk through the traditional method and the p-value method again. And so you're going to see very similar things, except for just some of the formulas are going to be a little different, right? We're going to use the t-score, the formula for a t-score instead of a z-score, and so on and so forth. So the calculations are going to be very similar but different, okay? So everything we're going to do is based on the assumption that we don't know the population standard deviation. Well, just like in confidence intervals, if we don't know sigma, we're going to use the sample standard deviation instead as an estimate, right? Okay, so now let me get my markers, and I have my calculator this time. So we're good there. Okay. So here is okay. So here's what we have. It says statistics students believe that the mean score on the first statistics test is 65. The statistics instructor thinks the mean score is higher than 65. To test his claim, he selects a random sample of 10 statistics students and obtains these scores. Okay, so here's the scores on the randomly selected students. 65, 65, 70, 67, 66, 63, 63, 68, 72, and 71. Okay, so these are the values that we have. Okay. Now he uses this data to conduct a hypothesis test using a 5% level of significance. So what does that mean? Alpha is equal to 0.05. And what's his claim? Well, he claims that the average score, the mean score, is higher than 65, right? So the claim, right, is that the average score, that's mu, is greater than what? Greater than 65, higher than 65. So this is the claim. So the claim is the alternative, right? Greater than. So the null and alternative hypotheses is then this. It's going to be mu is less than or equal to 65 versus mu is greater than or equal to 65, and this is the claim. Okay? Can everybody see that? Okay, good. So this is the claim. Okay? Now, again, this is going to be a left tail test. Okay? So now, step 2 is, again, always the same. We're going to assume the null is true. So in this case, we're going to assume that mu is equal to 65. Okay? So we're, again, remember, the null is that there's no change, right? So we're going to assume that the mean score is not higher than 65, but equal to 65. Okay? So now, step 3 is write down the information. So what information? Well, this is our information, right? So alpha is equal to 0.05. And also the data. Okay, so the thing is I would put this data, right, this whole thing into my list. Okay, so go ahead and enter that data into your list, L1. So remember, go under Calc Edit, and then choose Edit from the menu, and you choose one of your lists, and enter the data into your list. So what I'm going to do is I'm going to write in here L1 is equal to my data. Okay, so I'm basically just writing down where my data is located. Now, in this case here, they don't give us sigma, right? So we're going to use a t-distribution. So in this case here, the data, now it says the data are assumed to be from a normal distribution. Does the sample data provide evidence that the mean score for all students is more than 65? Okay, so now we don't know sigma, and even though it's coming from a normal population, we're still going to use the t-distribution because we don't know sigma. Okay, so now what actually the normal population tells us is that our distribution of x bar will be bell-shaped and symmetric. Okay, but because we have a small sample size, we're going to use the t-distribution. Okay, so but the main reason that we're going to use the t-distribution is because we don't know sigma. Remember, that's the decision maker. If we know sigma, we're going to use z. If we don't know sigma, we're going to use t. Okay, so we're going to use a t-distribution. So we know that t, let me use a different marker. So we know t is going to be how many degrees of freedom? Well, what's n? 11, right? No, 10. So 10, so the degrees of freedom is what? 9. So we could put t sub 9 here, so t with a subscript of 9, or you could also use t with parentheses, and you could use 9 inside parentheses. Basically just keep in mind that their degrees of freedom is 9. So you could also write it up here as if you put n equal to 10, then of course degrees of freedom is equal to 9. So, but this is the distribution we're going to use. So that means over here in step 4, we're going to use the t-test on the calculator. But before we do that, let me show you the traditional method and the p-value method using the t-statistic. So the traditional method, let me use a darker marker. Let me try purple. Yeah, there we go. So the traditional method, we're going to make our t star, right? So our t star value is going to be based on this formula. It's going to be x bar minus mu naught divided by s over the square root of n. And so now, how are we going to get s? Well, we're going to use one of our stats, right? That's how we're going to get our s. So we're going to use one of our stats on our data, okay? So let me plug the data into the calculator. Okay, so I'm going to go to Stat Edit, and I'm going to put in, so 65, 65, 70, 67, 66, 63, 63, 68, 72, 71. And so we got my 10, so now I'm going to go to Stat Calc, one of our stats, and I'm going to put in my list where my data is at. And so now I get x bar, so here's my x bar, right? So here's where I would put in my data here. So x bar from my one bar stats, okay, is equal to 67, and s is equal to 3.0 if you round it to the hundredths place. So again, I got all of this, I got from 1 bar stats on my calculator. Okay? So now that I have that information, now I can go ahead and use that up here. So now I've got x bar, which is 67. So it's going to be 67 minus mu naught, which is 65. And then s, which is 3.20, divided by the square root of n, which is 10. And so what do I get when I plug that into the calculator? Well, let's find out. .98. So, or actually 3 decimal places since it's t. Let's go 1.976. So 1.976 is what I get for my t star, my test statistic, right? So now the traditional method, I need to find what t alpha is, right? Now it's a right-tailed test, right? So in this case, I'm going to use inverse t. And so again, I need the area to the left. So what's the area to the left when it's a right-tailed test? And alpha, remember alpha is 0.05. So in this case, it's a right-tailed test. Alpha is 0.05, which means the area in the right tail is alpha. So that means the area to the left then is 1 minus that, so it's going to be 0.95. So I'm going to put 0.95 into my calculator. And then now, the next thing I put in for t, inverse t, is going to be the degrees of freedom, which is 9. So then, that's going to give me a critical value of, so go to second vars, go down to t, inverse t, 0.95, comma, 9, and I get 1.833. So 1.833 is my critical value. So that's step 4. Now step 5, what am I going to do? I'm going to compare, right? It's a right-tailed test. Oops, I put left tail. It's a right tail. Duh. It's a right-tailed test. Why didn't you guys say anything? Oh. So it's a right-tailed test. Okay, not left. Sorry, my bad. So arrow to the right, greater than, right-tailed test. So it's a right-tailed test. So I have, everything's correct. I wrote down a left when it was supposed to be right. So it's a right-tailed test. And so now, here are my critical values. And so since it's a right-tailed test, when am I going to reject? I'm going to reject when my test statistic falls within the rejection region, right? So greater than. In this case, if my test statistic, my t star, is greater than or equal to what? My critical value. So t star, which is equal to 1.976, and t alpha, which is equal to 1.833, is my t star greater than my t alpha? Yes. So therefore, what's the result of my test? I'm going to reject the null. And my conclusion, what's the claim? The claim is that the average test score for the first test for all students is greater than 65. So, in other words, since I reject the null, there is sufficient evidence, there is strong evidence, or there is significant evidence to support the alternative, which is the claim. So what I would conclude is at an alpha level of 0.05, there is strong evidence to support the teacher's claim that the average score for all students on this exam is greater than 65 based on this sample data. Okay, and that's what I would put. Okay, now that's the traditional method. Now let's go back and quickly do the p-value method. Okay, so the p-value method again is comparing the p-value with alpha. So in this case here, p-value is equal to the probability of having as extreme or more extreme of a test statistic. Okay, now, the thing is in this case here, we have, since we're going to use the t-distribution, the calculator for finding the p-value, which is t-CDF function, requires that you use t-star. Okay, so we can't put x bar into there. We have to use the t-distribution, so we have to convert x bar into a t-statistic. So we still have to calculate t-star. So we're going to use the fact that we found t-star, and t-star was 1.976, or 978, I believe. No, 976. Okay, good. So here's our t-star. So now the p-value then is going to be the probability that t-star is greater than or equal to, right? Greater than or equal to, it's a right-tailed test, greater than or equal to 1.976. So again, what's the probability of having as extreme or more extreme than the value that we got? Okay, so now we're going to use t-CDF. Now the first thing we need to do is lower bound, upper bound, and then degrees of freedom. Okay, so the lower bound here is going to be 1.976. Now the upper bound, you can use 10 to the 99th power, and that'll work just fine. So let's just do that. You don't have to go that high with the t-distribution, but it'll still work. So 10 to the 99, and then the degrees of freedom is 9. And so what do we get for the p-value? Let's go to tests, or excuse me, not tests, vars. So go to second vars, and we're going to go to number 6 for t-CDF. And so we're going to put in 1.976, comma, 10 to the 99th power, comma, 9, enter, and we get 0.0398. 0.0398. 0.0398. Okay, so now let's do our comparison now, right? So p-value is equal to 0.0398. Alpha is equal to 0.05. So now the rule is for the p-value method is p-value less than alpha? Yes or no? In this case, it's yes. So again, the result is the same. We reject the null hypothesis, and the conclusion is the same. There is strong evidence to support the teacher's claim that the average score for all students on this exam is greater than 65 based on the data and a significance level of 0.05. Okay, that's it. So now the last thing is, let's show you how the calculator works and how we can use both. So now the t-test on your calculator will give you both your t-star value, your test statistic, and your p-value. So let's use t-test. So t-test, again, you're going to have to choose whether you're going to put in data or stats. So here it's going to be stats. And then it's going to ask you for what the data is. Or excuse me, not stats. We're putting in data because that's what they gave us. So we're going to use the data option because they give us data. Okay, which means if we use the calculator, we don't need this because the calculator is going to do all the work for us. So all we do is choose the data option, and then it's going to ask us where is the data located. So you just put in wherever your data is located. So for example, L1. Okay, and then from there, all you have to do is put in your. It's also going to ask you for your null, right? What is your null hypothesis? So mu naught, right? You have to put in mu naught. It's also going to ask you for your alternative hypothesis. Your alternative hypothesis in this case is greater than mu naught, so it's going to be greater than. Okay? And of course, frequency, we're going to leave alone. So this is the only thing you're going to put in. You're going to put in data, where your data is located. So this is your input option. Where is your data located? What is your mu naught? And what's your alternative hypothesis? Okay? And then it'll give you the same value. So if you use t-test,
So let's use the t-test here. So go to stat, tests, it's number 2. And so we're going to use stats, or excuse me, I'm sorry, data. Data. And so mu naught in this case is 65. And the list, the list is where your data is located, so I'm going to put in where my list is located at. Mine's at L4. Frequency, we're going to leave as 1. The alternative hypothesis is greater than, so we're going to choose that. And then we're going to put in calculate. And so now I get a t value, a t star. My t star turns out to be equal to 1.978, and my p value is 0.0396. Now, notice that my t star value is a little bit different. Let me see what I got here. Yeah, so my t star that I got before was 1.976. My p-value was a little bit off too, but again, it's because the calculator doesn't have round off error, okay? So you'll always get, but again, it's not going to affect whether you get the correct answer or not, okay? So don't worry about that, okay? So you'll always get the correct answer if you, regardless of what you decide to do. Now, I like using the calculator for t-test, but again, realize why it works, okay? The traditional method or the p-value method, okay? So that's what we're going to do. So this is the function, t-test. Okay, so now let's do another example. Okay, so let me... see here. Okay, so here is another example. It says, it is believed that stock price for a particular company will grow on average at a rate of $5 per week with a standard deviation of $1. Okay? An investor claims that the stock won't grow as quickly. The changes in stock price are recorded for 10 weeks and are as follows. So here is let me skip that one. Let me come back to that one. Let me do one that uses stats. Okay, let me come back to that one. Let me use a different one that uses stat. Okay, here we go. So it says, an engineer at Duracell has designed a new battery for industrial use. The old style battery had an average life of 29.2 hours. The engineer claims that the new battery is an improvement over the old one, since the new design has a longer life. A sample of 20 new batteries finds a mean life of 32.3 hours with a standard deviation of 3.9 hours. Test the engineer's claim using a 0.01 alpha level. This is a great question. I like this one. So we got some differences here. So now, what's the claim? He claims that the new battery is an improvement over the old battery. So what's an improvement for batteries? It lasts longer. Longer than what? Longer than the old style batteries, which is known to be 29.2 hours. So the claim is that the average life of the new batteries is better. So the average life, so the new battery, right, So the new style of battery is better than the old. So what does this mean? It means that the average life of the new style is greater or longer, right? Let's use is longer than that of the old battery, which is 29.2 hours. So again, how do we translate this into symbols? Well, average life of the new, well, that's mu, right? Average, right? Is longer, right? What is longer than? That's greater. And then, of course, this is mu naught, right? So this is going to be the alternative hypothesis again, and it's going to be a right-tailed test again, right? So again, our null and alternative are going to be mu is less than or equal to what? 29.2 hours versus mu is greater than 29.2 hours. And this is the claim. Okay? And again, it's a right-tailed test. Okay. So step one. Step two, we're going to assume the null is true. So we're going to assume that mu is equal to 29.2, right? No change. We're saying that there's no change going from the old to the new. Okay? So we're going to assume that the average life of these batteries are the same. Okay. So now step three is writing down the information. So alpha in this case is 0.01. And the x bar, so the sample mean for the sample, well, let's break down n, right? So what's the sample that they gave us? A sample was 20 batteries, so they took a sample of 20 batteries. The average of those 20 batteries, the average life was what? 32.3 hours. And the standard deviation of those 20 batteries, which is S, is 3.9 hours. Okay? So notice it says that as a sample of 20 new batteries finds a mean life of 32.3 hours, okay, that's X bar. Then it says with a standard deviation. So the with tells us that the standard deviation is from the sample. So that's S. Okay. So now, what are we going to use here? Well, since we've got S, we're going to use a t distribution. And so the t has a distribution that's t with the degrees of freedom of what? Well, the degrees of freedom is equal to 19. So it's going to be t 19. So we're going to use this distribution. So then step 4, what test are we going to use? It's going to be a t-test. So let's use the t-test on our calculator, right? And so what are we going to put in? This time we're going to use statistics, right? The input is going to be stats. And then from there we're going to put in x bar, s, n, right? We're going to need to put in that. We're also going to need to put in mu 0 and the alternative hypothesis, which is greater than mu 0. So let's go. Now this may not be the order. I'm just putting them down from memory. So I know this is not the correct order. I know mu 0 is usually going to be up here. Okay? Okay, so, and just keep that in mind. Okay, so let's turn this on. Let's go to stat tests, t-test. We're going to use stats. And now mu 0 is 29.2. That's what we're assuming. X bar is 32.3. S is 3.9. N is 20. And our alternative hypothesis is greater than mu 0. And so now we hit calculate. And our T star equals 3.555. And our p-value equals 0.0010. Okay, so now we can either do the traditional method or the p-value method now. Okay? If we do the traditional method, we just need to know what T alpha is, right? So if we use the traditional method, then T alpha is going to be equal to what? It's going to be inverse T. And what's the area to the left if alpha is 0.01? Well, in this case here, it's going to be 0.995. Okay, and again, if you're not sure, draw your diagram and map out the areas. Okay, so the area to the left is going to be 0.995. Or no, it's not going to be 0.995. It's not going to be 0.995. It's going to be 0.99. And so then the degrees of freedom, and the degrees of freedom in this case is 19. And so what do we get for this case? We get $2.539. 2.539. Now, if we want to do the traditional method, then it's a right-tailed test, so we're going to reject if our test statistic is greater than or equal to our critical value. So T star, which is equal to 3.555, T alpha is equal to 2.539. Is our test statistic greater than or equal to our critical value? The answer is yes. So therefore, what are we going to do? We're going to reject the null. And so our conclusion is, at an alpha level of 0.01, there is strong evidence to support the claim. Why? Because we're rejecting the null. That means that there's evidence to support the alternative. And in that case, we're going to say that there is strong evidence to support the claim that the new battery lasts longer than 29.2 hours, okay? And based on the sample data, of course, okay? So now, that's what we were right. Again, if you don't want to do the traditional method and you just want to use the p-value method, then all you have to do is use the p-value and compare it to alpha. So p-value, which is equal to 0.0010, alpha is equal to 0.01, and of course p-value is less than alpha, and we get the same conclusion, the same result and conclusion. Okay? Okay, so now let's do, let me do another example. I want to do an example where the claim is the null. Let me see if I can find one where the claim is the null. Okay, let's see here. Okay. Okay, hold on 1 second. I'm just looking for an example. Let's do this one. Let's see here. Let me. Just want to make sure. I want to use one that. Okay, let's do this one. So this will be the last one. I just want to do an example where the claim is the null hypothesis because we haven't done that yet. So sorry for the pause there. So let's say we have this situation here. It says the National Institute of Standards and Technology provides exact data on conductivity properties of materials. Following are the conductivity measurements for 11 randomly selected pieces of a particular type of glass. Okay, so here's the data that we have. And so we get 1.11, 1.07, 1.11, 1.07, 1.12, 1.08, 0.98. I just want to make sure I'm not going off. So 0.98, and then we get 0.98, 1.02, 0.95, 0.95. So there's our data. And so we have 11 randomly selected pieces of a particular glass, and this is the conductivity. Okay, so now, using alpha equal to 0.05, does this data provide evidence that the average conductivity of this type of glass is at least 1? So at least 1. So they want to test the claim that the conductivity, right, so average conductivity is at least 1. And it says assume the population is normal. Okay. Now here's the thing. We don't know sigma, so we have to use a t-distribution here. So that's one thing we want to make sure we see. If we were given sigma here, then we would use a z-distribution because the population is normal, okay, even though we have a small sample size. But since we don't know sigma and we have to use s as an estimate for sigma, we have to use the t-distribution. So the claim here, it says average, so this is going to be mu, right? Average conductivity. The claim is that the mu is what? At least. Well, what does at least mean? It means greater than or equal to, right? 1. And so this is our mu naught. So now, in this case, this is the null hypothesis. So our hypotheses that we're going to set up is going to be that mu is greater than or equal to mu naught, which is 1. Versus mu is less than 1. And in this case here, this is the claim. Okay? So now we're going to do the hypothesis test using this as the claim. And notice that this is a left tail test. Okay? So now, let's use the t-test, right? So this is step one. Step two is we're going to assume the null is true, right? So in this case, we're going to assume the claim is true. So we're assume the null is true, or we're going to assume that mu is equal to 1. Okay, that's what we're going to assume. So 3, we're going to write down the information. This time they give us data again. So alpha is 0.05 in this case. Data, I'm going to put again into L1. Okay, and then what else do they tell us? Well, they don't tell us anything else. But since we don't know sigma, we're going to use the t distribution. So it's going to be t with how many degrees of freedom? 10, because n is 11, right? So the degrees of freedom is going to be 10. Okay, so that's what we're going to use. Oops, not equal to, we want tilde. So distribution is going to be t. And so now, what are we going to do? We're going to go use the t-test, right? So this is going to be step 4. And we're going to use t-test. And in this case here, again, we're going to use the stats. That's our input. We're going to use stat. And then we're going to put in our list, right? So our list is going to be L1, let's say. And then what we're also going to put in is our alternative hypothesis, which is going to be greater, oops, not greater than. In this case, it's going to be less than mu naught. And that's it. Okay, then we're going to calculate. So what do we get for our t star and our p-value? Okay, let's find out. Okay, so now what do? We go to our stat tests, use number 2 for t-test. Now I'm going to use stat data. So let's go to date. Oh, I'm sorry, man, I keep putting the wrong thing up. Sorry, guys. They didn't give us stat, they give us data. Sorry. This should be data, not stats. Sorry. Data. If we're using data, we use data. Okay. So data, and then mu 0. Oh, that's another thing I forgot. Mu 0. We got to put in mu 0. Right? So mu 0 is what? 1. That's what we're assuming. We're assuming that the conductivity is 1. Now let's put in the list. So first things first. So let's put in stat edit. Let's go back to stat edit. And let's put in the data. Okay, so the data is 1.11, 1.07, 1.11, 1.07, 1.12, 1.08, 0.98, 0.98, 1.02, 0.95, 0.95. Okay, so now I'm going to quit out of there. Now I'm going to go to stat tests, go to t-test, choose data, and then mu 0 is 1. Put in my list, mine is going to be in list 5. And then I'm going to choose less than for my alternative hypothesis. And then calculate. And so what do I get? I get 2.014. So 2.014 for my t star, my test statistic. And my p-value is 0.014. 0.9641. Okay, so now my test statistic is this, my p-value is this. So obviously from the p-value, I'm not going to reject the null. I'm going to fail to reject the null. So if we use the p-value, right, so in this case 5 So 5 is p-value is equal to 0.9641, and my alpha is equal to 0.05, right? And so is my p-value less than alpha? No. So I put a slash through it, so not less than. And so what is the conclusion or the result of my test? We fail. Therefore, we fail to reject the null. So what does that mean for our claim? Now here's where, when the claim is the null hypothesis, the only two conclusions that we can come up with is either we have enough evidence or we have strong evidence, significant evidence to reject the claim, or we don't have enough evidence or we don't have significant evidence to reject the claim. So it's either we reject the claim or we fail to reject the claim. So since here we fail to reject the null, and the null is the claim, we fail to reject the claim. So what I would state is for number 7, the final step for the conclusion, again, I would state at an alpha level of 5%, there is not enough evidence, right, because we failed to reject, there's not enough evidence to reject the claim that what? That the average conductivity is at least 1. Okay, that's the way we state it. Okay, so again, just make sure you do these examples, understand that. If you have any questions, reach out to me. Do the examples, make sure you get the correct answers, and next time we'll do confidence intervals now, not dealing with the mean, but not confidence intervals, I'm sorry. Hypothesis testing, we're going to now next time look at hypothesis testing involving the parameter P, the population proportion, and then we'll see how we handle that one. Okay, take care, have a great day.